So we are talking, section 8.1 is distribution of the sample mean. We're going to talk about sample means and sample proportions in this chapter. So first I have just a question to kind of start us thinking along the right lines. If I wanted to find the average household income in the United States, and I take a survey of 10,000 households, do you think the mean, the average of my sample, would be the same as the average of the entire population?
No.
Probably not. Okay, what if I go and I pick a different 10,000 households? Will that be the same as my first average? No. So how am I actually going to find this? How am I going to find this if every sample has different mean?
Sample everyone.
Okay, sample everyone.
Sample all 10,000.
Find the gross domestic product and divide it by how many houses people live in the United States.
Interesting. Way to think about it. Okay, so this leads us to a couple definitions we're talking about. When I'm talking about a sampling distribution of a statistic, it's the probability distribution for all the possible values for a sample of size n. Okay. Sampling distribution of statistic. Today, we are looking at the sampling distribution of the sample mean. So that would be a probability distribution listing all the possible values of the mean and looking at those probabilities. So those are the two definitions. So these are the steps we are going to go through. And we're going to walk through an example in detail here in a few minutes to kind of illustrate exactly what we're looking at. We will obtain a random sample of a given size. Find the sample mean. And then you would repeat all the steps until you had all the possible samples of that size. So we're going to walk through this on the next example. Kind of show you how to create a sampling distribution for the mean.
I think Miss Kelly asked to go down to the ag building for a class period last week or something.
Last week it was really bad one day.
It was like during 7th hour or whatever, or 8th hour. Miss Spring was talking about it to us.
Yeah.
Did she go down?
It was
Yeah,
awful
she
that
brought
day.
one of the ag building rooms for a class period.
Okay, let's look at this one.
Oh, okay.
So the population is the weight of 6 pumpkins in pounds displayed in a carnival game. Guess the weight game, please. You are asked to guess the average weight of the 6 pumpkins by taking a random sample without replacement from the population. Okay, so this carnival game has got 6 pumpkins here. You pick a random sample of a given size, and then based on that you have to try to guess the average weight of the entire 6 pumpkins. Does that make sense? So you would pick 2 of them, weigh them, get an average weight, and see if that matched. And then try to guess the total average weight. So we are going to first start out and calculate the mean of this and see what the true average weight is. So how would you find the mean?
I don't know.
All right, so let's add up all these weights. So that adds up to 84 divided by how many pumpkins?
Big pumpkins.
84 divided by 6. So that tells me the true average is 14 pounds. Now what we are going to do is create the sampling distribution of the sample mean for a sample of size 2. So I've given us a pretty small list to do that. If you would, I'm going to go to the next slide here in a second, but would you just jot down this table real quick? Or basically you just need to know each pumpkin and its weight. So if you just want to write A-19, B-14, jot those down before I change slides. gonna do this to try to draw some conclusions. Okay, so I have started a table, and we are going to fill in the gaps. So whether or not you write this down is completely up to you. But I have listed out all the possible samples of size 2. So that means you could have like A and B, A and C, A and D, A and E, A and F, B and C, B and D, B and E, B and F. Does that make sense? So I've started my table. These are my samples. I've got a couple left to fill in here. So I did all of the ones with A, all the ones with B, C, D. I could have D and E, or D and F. Or I could have E and F. Those are the ones I didn't have in there. Okay? So you don't necessarily have to write all this down if you don't want to. Let's fill in the weights on these. So A and E. Pumpkin weigh, A weighs, and E, okay, A and F would be 19 and, okay, B and E, B and F, C and F, D and F, and E and F. Okay. Now what I did is we need to calculate the average for each of these. So we've got 7 of them that I have done. So you guys do the A and E average. Girls do A and F, B and E, B and F, C and F. Now you two do D and F, and you do E and F, the very last one. So find your average for me. 14.5. Okay, what'd you girls get?
18.
All right, B and E,
12.
B and F,
15.5.
C and F.
16.
You thought what?
I thought we were doing B and E.
All right, D and F,
13.
and E and F. Okay. How many different combinations do we have up here? Let's count them. 15, don't we? So there are 15 combinations. So the probability of combination A and B would be 1/15, and the same for each of these, right? So I don't really have to write that down each time, do I? So each of those have a probability of 1/15. Okay, are you guys kind of with me so far? We just listed every single combination of 2 pumpkins, found the average weight of all of them. All right, so on the next slide, I've kind of changed it. I've listed the average weights that we got in order. I want the probability of each of these. So 9.5, that came up just one time, right? So it would be 1 in 15. 11.5, whoops, went the wrong way. 11.5 came up once. 12 came up twice. 12.5 was once. Okay, so let's see. This one was once. This one was once. This one was twice, so the probability would be 2 out of 15. Okay? 13 showed up once. 13.5 showed up once. 14 is once. What other one got repeated? Let's see, 14.5 twice. So all of these were 1. Okay. 15.5. Once. 16. 16.5. 17. None of the others are repeated, are they? So all these would just have a probability of 1/5. Okay. Do you guys understand how I got those probabilities? I didn't necessarily make you go through that step. You're going to do one here in a minute. But I just listed all the possible combinations, so every possible sample mean, how many times it came up. So, what's the probability that the mean is the actual population mean? What was the population mean? 14. So what is the probability that my sample would match that?
115.
Okay, here's the next question. What is the mean of the sample means? So I want you to add up all of your sample means here.
We divide that by 15. 14. No.
This adds up to 210. You guys get that? So if you divide it by the 15 different options, we got 14. But 14 is what? That was the population mean. So when I looked at every possible sample and found the average of all the possible sample means, I actually got the population mean. Interesting. Let's see. Okay, so the next one I'm going to put up here, and I want you guys to give it a shot. So it's a smaller table. I'm doing population or samples of. Oh, get close.
Oh no.
This is unfortunate. Okay. Okay, we're going to do samples of size 5. So I've listed out most of the combinations along with their weights, and I've already found the averages. I want you to come up with the last two combinations, list their weights, and find that average, and finish off this table for me. So I'm going to give you a couple minutes, and then we'll talk. So this one had an average of 14, and the second one had an average of 13. How many different combinations do we have? 6. So what's the probability of each of these happening? Okay. Why don't you guys real quick find the average of these sample means for me? So if you add up all of your y bars, divided by 6, what do you get? 14. So the average of these sample means is again 14. So what this is telling us is we've seen it happen twice now. If you had every possible sample and you found the mean of every possible sample and then you found the mean of those, it will always come out to be the same as the original population. Let's talk about the standard deviation a little bit. I am going to maybe draw something here. I'm going to do a very rough graph here. And I'm just going to be plotting like these means that we got. Okay, so the first one was when we had a sample of size 2, right? If I look through when we created this table, which I lost when my thing froze, the 9.5, we got that once. We got an 11.5. We got a 12 twice. 12.5, 13. I am just drawing this, not something that I would really ever have you do, but just so we can see if we can understand what's going on here. So I'm plotting all those sample means that we got the first time. Then the second time was when my n was 5. And so the means that we got out were 13.4, 14.8, 15, 13.8.
Wait, what do you do with those second dots?
I'm plotting the means from this table right here.
Oh,
14 and 13. Okay, so tell me, do you notice anything about how these compare?
The other ones are a lot less distributed.
Okay, my n equals 5, they were a lot closer together. What does that tell us about the standard deviation?
It's gonna be not as far.
Right, they're less spread out, so the standard deviation is smaller. So the first one is pretty spread out. What we saw is the bigger our sample size, the smaller our standard deviation will be. So a few questions about this. In this sample we just saw that there was less error. If you want to look at your probabilities, the probability we got the actual mean this time was 1/6 versus 1/15. So this was more accurate. So it was more likely to happen. They were less spread out, if you wanted to talk about that graph. Both times we found the mean of the sample means to be 14. So what did we decide about in the sample size? How does that impact our standard deviation?
the larger it is, the smaller the standard deviation is.
A larger n means a smaller standard deviation, or sigma. All right. So these examples are kind of twofold. First of all, to help you understand what the sampling distribution of the sample means really is. It's a mouthful, and we say mean a lot in there. But just taking every possible sample, finding the average at each of those samples. That's the sampling distribution of the sample mean. Second thing I wanted to see is what the relationship was with the mean and standard deviation in those. So that leads us to the next slide, which we definitely want to get this stuff down. It tells us something about the mean and standard deviation of our sample. So, the mean and standard deviation of the sampling distribution x bar, the mean of the sampling distribution is the same as the actual mean. The standard deviation will be equal to the original standard deviation divided by the square root of n. Sometimes that is called the standard error. The standard deviation might be called the standard. Look at an example involving this. The weights of pennies minted after 1982 are approximately normal, or approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. Find the mean and standard deviation of the sampling distribution of 200 simple random samples. You want me to give you a second to write? If you want to write down the problem, this is what I would probably write, this part. What would I find? So my mean, this is called the mean of x bar here, the mean of the sampling distribution. We know that is the same as the mean of the original. So what would that be?
2.46.
The standard deviation of the sampling distribution is the original standard deviation divided by the square root of n. So my original is 0.02 divided by the square root of 200. And we get, and that's all I need to do. Second one. Same thing, but this time we have 100 samples.
So the mean is still the same.
Mean does not change, still 2.46. Standard deviation is now what?
0.02 over the square root of
0.002.
I feel like I get it a lot more.
Good.
So the graphs were not.
Few things that we need to mention here. Is everybody okay with this example? Oh, we got that? If the original distribution is normal, which I told you this one was, that means the sampling distribution will also be normal. So the good news is we know how to deal with normal things. That was what our quiz was over Friday. So we know if it's normal, we get to read probabilities from the tables. So now, if I'm asking you to find probabilities of the mean being a certain thing, as long as the original distribution was normal, we can just continue reading our tables like we were before. So let's look at a problem. So the same scenario here, but my question is, I want the probability that in a sample of 10 pennies, we have a sample mean at least 2.465. So still dealing with these penny examples, but I want the probability that the mean of my sample will be at least 2.465. So I'm asking for the probability that the mean, so X
So we
bar,
can just look in this table for 2.46. Well,
not quite.
that's
To use the table, it has to be in terms of a z, doesn't it? So we know that our mean of the sample is what? The standard deviation is 0.02.
Over the square root of 10.
One thing I want to warn you, these standard deviations are going to be ugly. If you round that to just a couple decimal places, it will throw off your problem later on. So you can either leave it as 0.02 over the square root of 10, or if you want a decimal, you can do that, but leave me a lot of decimal places. Like I would leave 6 or 7. I'm just going to leave it like this for now. So I need to change this to a z. So I need probability that z is greater than or equal to. And remember, z is x minus mu over sigma, which we are using 0.02 over radical 10. So I'm going to type all that in. Really only need to go to 2 decimal places there, because when you read a z from the table, it only has 2 decimal places. Okay, remember the table gives you the probability that it is less than. So how will I find greater than? Okay, then you look up 0.79, and I get 0.7852.
So 0.264.
214, isn't it?
Oh, yeah, I'm not
That is our answer.
How will our problems be on our homework? How will they look?
Is that all we have left?
No, we've got more. They're going to be, I mean, some of them will just be find mean standard deviations, some will be kind of like this.
I didn't know if we'd have to do what we did at the very beginning with the big graph thing.
I just had you doing that so we could look at some results. Okay. Can I get you one more? The bells ring late anyway, right? I've got plenty of time. Bells are like a minute and a half off. Okay, last example for today. We are not done with this section, so there is no homework tonight. Tomorrow we will wrap it up and I will give you the homework. Okay, but we're going to do one more problem to finish this off for today. The engines made by Ford for speedboats had an average power of 220 horsepower and standard deviation of 15 horsepower. A potential buyer intends to take a sample of 4 engines and will not place an order if the sample mean is less than 215 horsepower. What is the probability that the buyer will not place an order? So he will not place it if the sample mean is less than 215. What is the mean of my sampling distribution? 220. Okay, how do I find the standard deviation of my sampling distribution? What's the standard deviation of the entire population?
15.
Over the square root of n. What is my n? How many engines are we looking at? 4. Okay, you could calculate this one. It does come out nice, just 7.5. So it changes to a z. So x minus mu over sigma. So I guess probably that z is less than negative 0.67. Less than is what my table tells me, so I just need to go to negative 0.67 on my table. And we get, so there's slightly over a 25% chance that this buyer will not actually buy the engines. Okay, any questions there?